All right, let's do a Physics 2 practice exam. So as per usual, this is my own exam that I've written myself to support students. I am not College Board, although I have written items for them. I've done a lot of work with P2 in the last year, so you'll know that the style is at least aligned. Now, for the difficulty, I tried to make it reasonable. We'll see how aligned that is. I will tell by the time of the video, really, because if I can get this done in the allotted time with me explaining everything, it's probably an appropriate difficulty. So we should see some easy questions, some medium questions, and some hard ones. So let's just get started. I do think of all the exams I've written, I do like this one the best. I think I did a good job of hitting all the P2 topics. So usually we like to start with an easy one. So two negatively charged spheres are placed along the y-axis as shown. Which of the following vectors could represent the E field at point P? Well, of course, this involves superposition, so we should just look at what all of the electric fields individually are doing. So my negative charges are sinks, right? Because the electric field represents the way a positive charge would go if you placed it at that location. So positive charges would get attracted to the negatives, which is why we say that they are sinks. So we see that just by adding forces, our two E fields are going to cancel vertically, so positive charge would get dragged directly to the left. So again, I'm going to sort of rate these as we go. So I think this is pretty solid in the easy category. All right. A pulse propagates along a uniform string of fixed mass under tension Ft with speed v. The string is then stretched to twice its original length. While the tension is the same, what is the new speed of the pulse? Well, if you got tension and speed on a string, we know that we're talking about wave speed. So we can try to decipher where that is on our formula sheet. So we're going to go to the waves section. And here I see this expression that says v on a string is equal to the square root of Ft divided by mass per unit length. And this is hard to tell functional dependence just right off the bat because we have this mass per unit length on the denominator. So it might help to just sort of get rid of that compound fraction and maybe write this as Ft times L divided by M. So it says the string has fixed mass, so mass does not change. The tension remains Ft. The string is stretched to twice its original length. So we have doubled the numerator, but we're under a square root. So my new speed is just going to be square root 2 of the original. Due to the fact there was a little bit of manipulating happening in the square root, I did actually bump this to a medium. Although it's not terribly hard. You could definitely argue that's a level 1. We'll see that my cutoffs are sort of a bit lower for P2 because on average in P2 we're not trying to write as involved math items. All right, back to the land of charged spheres. We have 3 charged spheres placed along the x-axis. Each set of adjacent spheres are separated by d. What is the net force F on the plus q sphere? Well, just like with the E field, we're going to use superposition. So we know that we're going to experience a force from the 3q charge. So of course this is Coulomb's law. So we know that the 3q is going to repel. It's going to repel our positively charged sphere, whereas the 4q is going to attract. And actually we know that the 3q repulsion is going to win because even though the charges are nearly the same, we know that that inverse square law is going to dominate. So here we're using the fact that the electric force, we're just going to sum up the kqqq over r squareds. So let's figure out what those are. Well, for my repulsive force to the left, or in the minus x direction, I have k times q times 3q divided by just 1d squared, right? Because the distance between the adjacent spheres is d, so this is d, and this is also d. But then for the repulsive, or sorry, the attractive force in the plus x direction, It's K. I'm still looking at the sphere of charge Q, but now I have to deal with the 4Q, and that distance is 2D, but that entire object gets squared. So we're going to have to do a bit of algebra. And I get 3 KQ squared over D squared left. And then I get 4 KQ squared over 4D squared, right? Because you had to square the 2 also in that denominator to the right. So our net force is just going to be 3 KQ squared over D squared minus 1 KQ squared over D squared. So we just get 2 KQ squared over D squared. And that is to the left. So that gives us answer choice C. There's some manipulating involved, so this was 2-star. All right, gas in a sealed container has initial volume V. Consider each of the following processes in which we expand the gas to a volume 2V from the same state. So we either expand the gas isothermally or we expand the gas isobarically. We want to compare the temperature in each case and the work done by the gas. Okay, as expansion occurs. Now, anytime you see the iso words, we should definitely say what they are. So isothermal is same T. Isobaric is same P. That's important to note. So let's try to draw both of these on a PV diagram to try to visualize. So first, for our process 1, this is probably the harder of the two to draw the isotherm for, but first we're just expanding from a volume V to 2V. We should know that an isothermal curve just sort of looks like this. An isotherm looks like that, whereas in case 2, we have an isobar. So like we'd know this was V0, this was 2V0. And then for my isotherm, or sorry, my isobar, constant pressure, so I can't change. So that's a flat horizontal line. So the work done is the area under the curve. So notice, if we try to take the area under these, it's clear that the isobaric curve just has more area because the graph is always taller. So we know the work done is actually greater in the second case, so W2 is bigger. And then what about temperature? Well, we know that case 1 has a constant temperature. So this is same T. But here, we see that if we look at our ideal gas law, PV equals nRT, we see that we have a fixed pressure. So pressure is fixed, but volume increases. So what does that mean? Well, that means temperature goes up. So that means that our answer choice would be D, because our area is larger in case 2, and our temperature increases in case 2 while it stays constant in case 1. So based on the amount of time this took, you can probably guess I'm thinking this is a hard one because you had to do a lot of synthesis here. We had to think about this. And I'm sure there's alternate ways you could have done this. All right, now a refresher. After that hard one, we got what I think is an easy one. Consider the bar magnet shown below. What is true about the magnetic field at point P with justification? So what do we know about magnetic fields? The fundamental rule is that magnetic fields form closed loops. And we know that outside a bar magnet, north poles are sources. So to form a closed loop, I have to be to the left inside the bar magnet. And the justification is nonsense, the other one, right? So the fundamental property of magnetic fields is that these field lines have to form closed loops no matter what. So left is our answer. A ray of light traveling in a vacuum is incident at 37 degrees with the normal of a gel block. And it says the refractive index is 1.2. We will put that over here. The ray then reflects from the boundary of the gel as shown. What is the angle phi of reflection inside the gel? Now, you can actually do this without math. Because what we notice about this is I'm going from a low index to a high index. So if you go from low index to high index, you bend towards the normal. So I actually know that we're going to bend towards the normal. I'll actually draw it like this. We're going to bend towards the normal. And then we also know that if we're reflecting off the gel surface, angle of reflection equals the angle of incidence. So it's going to be that same angle from the normal. And if I'm bending towards the normal, that theta is decreasing. So it's actually the only choice here where the angle goes down. Because if you bend towards the normal, that angle's decreasing. So we know it's that. But how do you do it quantitatively? Well, you just use Snell's law, right? You just use Snell's law. N1 sine theta 1 equals N2 sine theta 2. So we'd get sine 37 degrees equals 1.2 times sine theta 2. So theta 2 is just the inverse sine of 37 degrees divided by 1.2. And that's roughly 30 degrees, just to check. I actually put this as level 2 because you had to know that the reflection angle is the same as the refraction angle in this case, because it refracts, then reflects. So you had to know that it's this theta right here. So there's a lot of like trying to get you to do the complement, right? These are complements and 60 is complement with 30. Pretty standard. All right, the two resistors described below are made of the same material. Resistor 1 has length L and radius little r. Resistor 2 has twice the length, twice the radius. We're comparing power. Okay, well, we have three expressions for power. We have the definition, which is usually not helpful. We have I squared R, and we have V squared over R. Now, this is a series circuit. So since this is a series circuit, we know that we have the same current. So if we have the same current and we're comparing power, we should probably use I squared R. Because then we can just really be comparing the R's. So let's do that. Well, what's our formula for resistance? Well, resistance is equal to rho times L over A. So this means our second resistance would be, well, we have the same material, twice the length, and twice the radius. So pi r squared, you have to square your radius down there. So this means our radius, our resistance 2 is actually half of R1. So even though you doubled things that were on the numerator and the denominator, we had to remember the area was squared. So same power, same resistance. No, I'm totally wrong. Same current in series. Maybe not times 1, we'll say this is just the same. But the resistance got halved through resistor 2. So the power in resistor 2 is just half the power in resistance 1. Lots of manipulating here. 3 stars. Two charged spheres holding equal and opposite charges plus or minus Q are placed at opposite vertices of a square. What is the net electric field at the center? So if we look at the center, we see that this negative charge is going to be a sink, and this positive charge is going to be a source. So we have additive fields at the center, and we just want the magnitude, so there's no trigonometry weirdness here. All we need to do is just get the distance. So we know that the net E field is just going to be twice the E field from one of the point charges, which is 2 times KQ over R squared. And what is R? That's the only thing about this problem you have to figure out. So what is this distance? Well, this distance is S over 2. This distance is S over 2. So this distance is S over 2 times square root 2. Or it's also half the diagonal. So you should know that the diagonal of a square is S root 2. And then you just divide it by 2. So you get 2 times KQ over 1/2 s root 2 all squared. And that would be equal to, let's see, quarter, half. This is going to be the answer with 4 in it, because 1/2 squared is a quarter, then you got a 2, so you're dividing by a half. Yes, you get 2 times 2, which is 4 kq or s squared. I thought this was level 2. The diagonal thing gave it like a tiny twist. All right, consider the following 2 stars of the same surface area, which are modeled as black bodies. So that tells us that this is black body radiation. We want to compare the power P emitted by each star, and we want the peak wavelength emitted. Well, power, we know this is the Stefan-Boltzmann law, that the power radiated is proportional to T to the 4th. So this just says that as your star gets hotter, the average power increases. That should be pretty obvious, right? If you have a hotter object, it should be dissipating or radiating more power. And then what about the peak wavelength? Well, this uses Wien's displacement law, which says that the peak wavelength is equal to some constant divided by the temperature. So this says that as T goes up, lambda peak goes down. So the hotter star, which is Y, the hotter star should radiate more power, and X should have a larger wavelength. So that's C. Because again, if we talk about energy, it is short wavelengths that are more energetic. So that means that more of Y's spectrum should be shifted towards short wavelengths. So that's why X has the bigger wavelength, because we have our little like spectral intensity curves. There were 2 distinct concepts here, so this got bumped to 2. All right. The period of an EM wave is 2 times 10 to the minus 10 seconds. What is its wavelength? Well, it's an EM wave. What do we know about EM waves? Well, EM waves, we know that the speed of an EM wave in a vacuum, which is implied here, is c, the speed of light. And we also know that for a wave, traveling wave, v equals lambda f. So c equals lambda f. So that means that the wavelength is just going to be c times the frequency, or c divided by the frequency. All right, we don't have the frequency, we have the period. So we also need to do the substitution that frequency is equal to 1 over the period. We have that reciprocal relationship. So it's equal to just c times t. So c is 3 times 10 to the 8th. T is 2 times 10 to the negative 10th. So we get 6 times 10 to the negative 2. Yep, that's an answer choice. And our answer should be in meters, because we get meters per second times seconds. I thought this was still level 1, even though there was a substitution in there. All right. A small charged sphere moves at constant velocity in the plus x direction between 2 charged plates as shown. In the region between the plates, there are mutually perpendicular E fields and B fields. They're uniform. Constant velocity is our velocity selector. So this is telling us that the fields are balancing. All right, well, first of all, the easy field to get is the E field. Source to sink. So E field points in the negative y. And interestingly enough, we don't have to tell you if this sphere is positive or negative. We'll just pretend it's positive. A similar argument works for the negatively charged version. So positives accelerate with the E field. So there will be an electric force down. But this is a constant velocity situation. So Newton's first law says that there must be a force balancing the electric force, which should be our magnetic force. So that means the magnetic force is up. So using a right-hand rule of your choice, you can figure out which way the B field must point. So we know it has to be, we know we're going to make some sort of XYZ coordinate system here. So I like the rule that says stick your thumb in the direction of V, put your fingers in the direction of B, and then your palm points with F. So my palm needs to point up because I'm pushing my charge up with the magnetic force, and my velocity is right. So if my palm is up and my thumb is to the right, that means my fingers are pointing at you or into the screen. So that would be the magnetic field into the page. So it's minus Z. So minus Y and minus Z makes the answer choice B. Velocity selector is safely level 2 if it's qualitative like this. All right, the current I through a cylinder as a function of potential difference is shown. What is the equivalent resistance when two of these cylinders are connected in parallel? Well, two identical cylinders in parallel, we know that Req is just 1 over R plus 1 over R to the negative 1, which is R over 2, right? Equivalent resistance decreases in parallel. So that means we just need to get our resistance, and we divide it by 2. So Ohm's law, pick your favorite form of Ohm's law. R is equal to delta V over I. So it's actually not the slope of this graph, it's the inverse slope of it, but we can just take delta V over I anyway. So I see delta V was 5 volts, and I was 0.5 amps. Right, I'm taking my delta V on top. So this is not the slope of the graph. So I might just say this is 1 over slope. So I get 10 ohms. So if one of my resistances is 10 ohms, the parallel equivalent would be 5. This was pretty straightforward, but it still involved interpreting a graph, so I gave it level 2. Oh, this one. Lovely. We love thermo. Okay, suppose n molecules of a monatomic gas are confined to a vacuum-sealed container of height h and area A. We have a piston on top, and the piston is in equilibrium. We want the kinetic energy of the individual gas molecules on average. All right, so what do we know? Well, this piston is in equilibrium, so we know that if I draw a free body diagram for the piston, the weight of the piston, mg, must be exactly balanced by the force from the gas. And what is the force from the gas? Well, pressure is force over area. So we know that P times A is equal to M times G. So that might be helpful for us later on. So we know this is an equation we get from our balance forces. Then what else do we know? Well, we want average kinetic energy. So we have this expression that says the average kinetic energy is equal to 3/2 times the Boltzmann constant times T. Okay. So it looks like we need to just somehow get an expression for Kb times T, because I don't see any Boltzmann constants in here. But wait, we also know PV equals not just nRT, but equals n kBt. I see. Okay. We're going to get really into the weeds here with a bunch of gas law substitutions. This is one of the hardest items, by the way. Okay, so this tells us that this quantity, kBt, that we're interested in, is just going to be PV divided by capital N. So this tells us that our average kinetic energy is just going to be 3/2 times kBt, which is equal to 3/2 of PV divided by capital N, which is equal to 3/2 times, well, we can get an expression for P using our force balancing equation. So P was just mg over A. And then finally, what is the volume of this container? Well, the volume of this container would be its cross-sectional area A times its thickness H. So we get mgh, so 3/2 mgh over N. Wow. Good job if you got that one. There's kind of a sneaky solution you can do to this in a lot less steps than I did, where you use the internal energy equation 3/2 nRT, and you divide by capital N. There's sort of that variation as well. Yeah, this is super hard. Not this one, though. Object is placed beyond the focal length of a concave mirror. What type of image do we get? Well, let's ray trace. If I enter parallel, I bend through the focus. If I enter through the focus, I exit parallel. All right, that's an inverted image because the rays actually touch. One star. All right, two systems of charges are arranged into an equilateral triangle. We're comparing these two potential energies. So what is the potential energy of point charges? Well, we have U equals the sum of all pairs of KQQ over S to the first power. So sign matters here, right? Because if you have opposite charges, they are in energy debt to one another. So Q and Q, those aren't in debt. Those want to get away from each other. So that's +1. Q and Q, those want to get away from each other. That's +1. Q and Q, they want to get away from each other. So that's +1. So the energy of system 1 is 3 KQ squared over S, if we want to do that. All right, what about this one? -2 and -2. Those want to get away from each other. So they are not in energy debt. They want to get away. That's +4. -2 and -1. Those want to get away from each other. 2 and -2 and -1 make 2, +2. Then -2 and -1, we said was +2. So this energy is 8. So we see that both of these systems have positive potential energy. So there's not going to be a negative in the ratio because both of these systems cost energy to be assembled. And we see that, how do I get to 8 from 3? Well, I need to multiply by 8 and I need to divide by 3. This is level 2 because you have to be able to know what's going on with the signs. Okay, this is one of my favorite items, actually. Consider the following 3 sound waves. So first we have the pressure. The gauge pressure varies according to this cosine function. Then we are given a wave whose wavelength and speed are known. Then we're given the pressure as a function of time. Okay. Which pair of waves will have the greatest beat frequency? So once again, consulting our formula sheet, F beat is equal to the difference in frequency. So we're just looking for greatest difference in frequency. All right. So one thing we know, if we look at our formula sheet for this sort of wave 1, we know that the constant in front of t inside a wave is equal to 2 pi f. So we actually know that 480 pi is equal to 2 pi f. So this means f1 is just going to be 480 pi divided by 2 pi, which is 240 hertz. So 240 is our first wave frequency. Then for our second one, sound wave has wavelength 1.5 meters. So we're just using our wave speed equation. So I just divide v by lambda. So that's just 390 divided by 1.5. Yes, I do need a calculator for that. If my Desmos will load. 390 divided by 1.5, 260. So we're already getting some different frequencies here. So I'm going to pull this over a bit just so we can see. And then lastly, we have wave 3, which is this wave. So I see that it is repeating every 0.004. So the period is equal to 0.004 seconds. So the frequency is 1 over the period, which is equal to, I'm going to guess this is 250, just based on the fact that there's a 4 involved. This makes me think of like 4 in the 25% idea. Yeah, it is. All right, so we have 250, 240, and 260. So frequency is the greatest, the difference is the greatest between 1 and 2. Because that difference was 20 hertz, 1 and 3 was 10 hertz, and 2 and 3 was also 10 hertz. 3-star, not because anything was challenging, but because it was a lot of things. All right, region of space contains uniform, magnetic, and just a uniform B field, actually. We want the displacement D of the sphere. So this is clearly a circle, or at least a part of it. It looks like a semicircle. So we just have to do some solving. So anytime you have this sort of setup, we know that our magnetic force is supplying a centripetal force. So QVB equals mv squared over r. So QB equals mv over r. So r is equal to mv over qb. So this is the radius of the path, but we don't want the radius. We actually want this sort of displacement. And I did name it d for a reason, right? D is just the diameter because it exits along a semicircle. So it's 2 times r, which is just 2 mv over qb. All right, this is a pretty standard P2 skill, so I'd call that level 2. All right, 3 possible energy levels of an electron are shown. So this is sort of our Bohr model of hydrogen, thinking about that sort of thing. Which of the following statements is false? All right, so transitioning from 3 to 1 produces the greatest energy. Well, if I go from 3 to 1, I'm definitely falling the most rungs on my ladder, right? Think about this as like height. So if I drop a ball, yeah, its speed would definitely be the greatest if I drop it from 3. If I go from 3 to 1, is that the photon of greatest frequency? Well, we know that E is equal to HF. So yes, if F is the greatest, then E is also the greatest. The electron atom system has the greatest potential energy in n equals 1. Well, that's just not true, right? Negative 10. Negative 10 is not the biggest number here, so the answer is C. And is 2 EVs required to go from 2 to 3? Why, yes, it is, right? If I give 2 EVs to an electron in level 2, negative 6 plus 2 is 4. I thought this was easy. Level 1. A sealed chamber whose volume we know contains a monatomic gas, whose pressure we know. What is the internal energy of the gas? What is internal energy? Internal energy is U for monatomic ideal gas is 3/2 nRT. But we don't know T or the number of moles. But what do we know? Well, we know pressure and volume. So we also know PV equals nRT. So I can just replace nRT with PV, and that gets us our internal energy. So what is P? P is 8 times 10 to the 5th. What is V? V is 5 times 10 to the minus 3. Let's see. We're going to get like 4, then a 2, and then a 6. It's the answer that starts with 6. Yeah, 6,000 joules. One substitution makes this level 2. All right. This might be excessive. Sorry about this one. In the circuit shown below, find the power dissipated by the 2R resistance. This is just a whole bunch of circuit analysis. Well, we know that what makes this easier is just to find REQ. So first what we can do is we know that 4 and 2 in series makes 6. So maybe I'll just do a quick redraw up here. And then REQ for this would just be R plus 3 and 6 in parallel. And 3 and 6, at this point, we've seen enough to know that that's going to be 2. 6 plus 3 is 2 in parallel, so we get 3R. So why does that help? Well, that helps because this tells us that the total battery current would be the battery EMF divided by REQ, which is 3R, which is 1/3 times script E over R. So this tells us that anybody in series with the battery gets that full current. So that means delta V equals IR. So I will drop 1/3 of the battery EMF across this object, which means that I will drop 2/3 of the battery EMF across this object. This is not the only solution, by the way. You know what? Let's actually not do it this way. Let's go back to this sort of intermediate circuit, because if we want to find the power dissipated by the 2R resistance, which is in this sort of branch, we can do it just by finding the current through this branch, because we know the current will be the same via the series rule. So we know that we know that the current is just equal to delta V over R. So for this sort of 6R branch, we're dropping 2/3 of the battery voltage, and the resistance down that branch is 6R. So we get 2/18, which is 1/9. Script E over R. So now we can just find the power dissipated by the 2R, because power is just I squared times R, and I squared times R is just going to be 2/81. Yeah, sorry about that. I needed a hard circuit analysis, so I had to put a couple things in here. I would not expect this many steps, but it's a good mental workout at least. So there's our halftime break. So we look basically on pace. So this seems to be kind of appropriate, where there's some easy ones and hard ones. This is probably excessive. All right, when an object of height h0 is placed from a convex lens, we get an enlarged real image that looks taller, basically. What can be said about X? So this is asking, where can we place the image? Where can we place the object to get an enlarged real image? Now, this is a fact. Now, if you know this is a fact, you know the answer is if you place it close to the lens, but not too close. This is getting close to the focal point, but not too close that you don't get a real image anymore. But just to actually prove this, you know that if you go beyond the focal length, it's just not going to work out. Like the rays don't actually sort of collide there, right? It's virtual. So we know it's not in this region. We also know far away. It doesn't work either. This is kind of just a fact. I'm putting this at level 2. You can ray trace each of the cases and do this. Now, another way you could do this, which is probably the more accessible way, is figuring out when the sort of thin lens equation outputs this result. So you can actually check when does the sort of cutoff occur. So when is it true that di equals do? So if you have 1/di plus 1/do equals 1 over focal length. So when is the cutoff there? Because we know magnification is just the ratio of these distances. So you can just set 1/do plus 1/do equals 1/f, and you would see that 2/do is equal to 1/f. So do would just be equal to 2f. So you can see that 2f is actually the cutoff distance here, because 2f is when you get no enlargement or reduction. So I would say this is level 2. Borderline level 3, but this is kind of just a fact. All right, in the scenarios shown below, charged spheres are placed along the x-axis. Assume all these tick marks are equally spaced, and potential is 0 far away. Potential at P is V1 in scenario 1, and it's V2 in scenario 2. We want the ratio. All right, so what is V? V is the sum of KQ over R. So let's just do that for each of these. So this is, again, your height map. So at point P, this would be contributing a factor of +1 to the potential because it's a hill 1 unit away. And it's still contributing a factor of +1 when you're 1 unit away. Scenario 2. And now if we look at what's happening with the addition of another charge, well, we still have a hill. It's still going to add to the height, except now we're sort of 2 units away. So this would be adding a factor of +1/2. So the potential in scenario 1 is essentially 1. And the potential in scenario 2 is 3/2. So what is the ratio of these two values? Well, we want V2 over V1, which is 3/2 over 1. You couldn't really figure that out without doing some math. Now notice that this answer is baiting you into thinking there's a squared in the denominator. All right, magnetic field. We have these two current carrying wires. We want to find where between these two wires is the field 0. So we can check that the field should be 0 because if I right-hand rule, so I stick my thumb and I curl my fingers around it, I get an into the page big B field here, and I get an out of the page smaller B field here. So we know that sort of to cancel the big B field that's into the page, we have to be farther away from that wire. So the point of interest needs to be like somewhere over here is going to be like our distance. So how can we find that? Because there's two options. We know it's not either of the ones that are closer to the big wire. So what we know is that if you are a distance x from one wire, you're going to be a distance d minus x from the other. And we also know the formula from a wire, so we're just going to set those two equal. So we're just going to set the magnetic field from the 4I equal to the magnetic field from the 1I. So B from a wire is mu naught I over 2 pi r. So we get mu naught times 4I over 2 pi x is going to equal mu naught times 1I divided by 2 pi times the quantity d minus x. Now a whole bunch of stuff cancels, and this equation turns into 4 over x equals 1 over d minus x. Flipping both sides over gets, or cross multiplying rather, is probably easier. We would get 4 times d minus x equals x. So 4d minus 4x equals x. So 4d equals 5x. So x is equal to 4/5 d. What did I rate this one? 23. This is level 2. I think this is borderline 3 because of the algebra. A string fixed at both ends has its first harmonic at F1. What's the second harmonic? So this is something you just need to know. This is on our fact sheet. You could draw out the standing waves, but if you can do that, just memorize this. What do we know? So this is fixed at both ends. So this is closed, closed. If you have closed, closed, the allowed frequencies are F1, 2F1, 3F1, ... So that's going to be C. Level 1, you just had to remember this fact, that if you have closed at both ends, or if you have open closed, the harmonics are just 1, 2, 3, 4 times the fundamental frequency. Now the weird one, that's the open, open. Open, open is the weird one, where you get sort of the odd 1, 3, 5 numbers. Oh man, 25. This is absolutely the hardest, most involved one. When I saw that I was going to write about Compton scattering, I knew it was going to be rough. I feel like there's not really an easy Compton scattering question. All right, so we have a photon hits an electron, and the photon zooms away. We want to find the energy of the photon after the interaction. Okay. Well, this is Compton scattering. If you see this picture, you know it's Compton scattering. There's like no other version of this. So at least for pattern recognition, it's not bad. So we know that the change in wavelength of a photon in a collision is given by Planck's constant divided by mass of the electron times speed of light times 1 minus cosine theta. These are all constants, but our cosine is just of 37 degrees. So we can work out what that is using all of our great values here. So Planck's constant, it's like 6.6 times 10 to the minus 24. Sorry, we have to see me Desmos this live. Divided by the electron mass, 9 times 10 to the negative 31. Speed of light is 3 times 10 to the 8th. And then we have, 34th for Planck. And then we have 0.2 for this. So we get 4.9 times 10 to the negative 13th meters. So this is how much the wavelength of the photon changes by. What we want is the energy of the photon after the interaction. So this is just the change in wavelength. We were given the original wavelength. So we know that longer wavelengths is lower energy. So the new wavelength is the old wavelength plus the delta lambda. Because if your wavelength increases, your energy must have decreased, right? Because energy was sort of lost or transferred in this collision. So our initial wavelength was 6 times 10 to the minus 12th. Our delta, our extension factor was this. So we can just add on 6 times 10 to the minus 12th. And I get 6.5 times 10 to the negative 12 meters. So this is still not my answer. This is just my new wavelength. And then I have to connect to the photon relationship that E equals Planck's constant times frequency, which is equal to Planck's constant times C over lambda. So I just plug in HC over lambda. I'm sure this is riveting content, just watching me write all of these fundamental constants and substitutions in there. But this is a rough question. Compton scattering is just kind of rough in general. Trust me, we get A. So you can just trust that we get A out of this. 3.1 times 10 to the negative 14th joules. Now you can see that that makes sense because we get sort of negative, what is this, 34 and 8 is like 26. Yeah, you get 26 and 12, which makes 14. So just kind of scanning our answer, that makes sense. Absolutely 3 stars. This is the hardest one, in my opinion. All right, gas undergoes this PV diagram process from X to Y. It is adiabatic, so anytime you're given a gas word, we should underline it. What is adiabatic? Adiabatic is no Q, no heat transferred. What is true about the work done by the gas on the surroundings? So what is the gas trying to do? Well, the gas is pushing on the container, trying to push the container out. So we know that the work done by the gas is equal to P times, I should actually say by. The work done by a gas is P delta V. Well, it's really like an integral or a calculus idea, but it's really the area, P delta V. It's the area under this PV curve. So what's going on here? Well, notice that my gas is expanding, right? We're going from V0 to 3V0. So if my container is expanding, that means the gas is doing what it wants. So if the gas gets its way, the work done by the gas is positive. It's doing positive work. And why is that? Well, because the gas is trying to get the container to expand. So it's not about the pressure, it's about the volume. You had to know a couple things here. I was trying to bait you into thinking adiabatic was 0 work. So that's why I picked 0. I tried to make it a bit easier by making you not pick between positive and negative because I thought that was it's a bit mean playing the like sign game with work. Oh, actually I lied. This is my favorite question because it's accessible yet kind of interesting. So we have plotted the electric potential at various points in this circuit. So we've given that at point X, the potential is equal to 12 volts. At position Y, the potential is equal to 8 volts. And at position Z, the potential is equal to 0 volts. Cool. We've also given some info about the currents. The current at Y is 1 amp, and the current at Z is 3 amps. And what we want to do is calculate the resistance R. Well, if we want the resistance R, that means we need to know the other things about the resistance. So we know that Ohm's law, delta V equals IR. So R is delta V over I. So we just need to find delta V and I across this resistor. So because we color-coded our potential, it's actually super easy to get delta V. This is just Kirchhoff's loop rule. How do I get from 12 to 8? Well, 12 to 8 is, of course, 4. And then what's the current? Well, then we just do another of Kirchhoff's rules, right? Because we see after the branch splits, we have 1 amp and 3 amp going down the branches. So that 1 and 3 amp can't just spawn from nowhere. It must have came from the battery. So our total current is going to be 3 plus 1. So our voltage drop was 4 volts. Our total current was 3 plus 1 amps. So we get 4 over 4, or just 1 ohm. I like this one. This is medium. You got to do both Kirchhoff rules for this, but I thought this was very fair. All right, more about potential, actually. Consider the equipotential diagram shown below. So we have these 3 different curves. Now, I always like to color these as well from high to low. So we have high potential. We have medium potential. Bear with me here on my bad coloring skills. I'm trying to get us out of here in a reasonable amount of time. And we have low. All right, so what we want is we're placing a charge at point O is positive, and we want to find the absolute value of the work done required to move the positive charge to each of the points. So we know that the work done by an external force is equal to delta U, and delta U is Q delta V. So all we're doing is we're just looking at the delta V. So delta V from O to A. O is at 1 volt, A is at 2 volts, so that's plus 1. Delta V from O to B. Well, B and A are on the same curve, same color, so that's also plus 1 volt. And then what about O to C? Those are actually on the same curve, so there's no potential difference there. So it costs no energy to move to C, but it costs the same amount of energy to move to A and B. C is last, A and B tie. Pretty sure I called this 1. Yeah, I did. Because all you had to do is just count delta V. Oh, nifty, a double lens. All right, 2 convex lenses, X and Y, each have the same focal length F and are separated by distance 2F. We place an object of initial height H, 3F from the first lens. We want to find sort of the final height of the image after it goes through both lenses. Now, you could do this totally like without drawing it, but where's the fun in that? Enters parallel, goes through the focus, enters through the focus, goes parallel. So I'll delete those in a second here. So that's my first it's my first one here. And then notice we're going to get a sort of magnified upright image from Y when we do this. Okay, so I think we'll just go by solving this sort of in a chain. So we know we're just doing thin lens equation. So this is lens X. So 1 over the object distance, which was 3F, plus 1 over the image distance equals 1 over the focal length. So we know that 1 over DI would be equal to 1 over F minus 1/3 times 1 over f. So we'd get 1 over di equals 2/3 times 1 over f. So di is equal to 3/2 f. So what that means is that we can go over here and we can say that this distance from x is 3/2 f. So that means our distance from y must only be 1/2 f, because we said the two lenses were spaced by 2f. So this means that we can just thin lens once more with f, or sorry, with the lens y. So our new object distance is f over 2, solving for our image distance. And then looking here, what do we got? Sorry, so we got 1 over di is going to be 1 over f minus 1/2 1 over f, so we just get 1/2 times 1 over f. So di with a negative sign. No, not with a negative sign. No, we do get a negative sign, sorry. No, this is just negative 1 over f. I can't do math. So we get di 2 over f, yeah. So di would be equal to negative f. Oh, sorry, I had a mental thing there. So all of this is to say, we now can just do our magnification. So our total magnification is going to be the magnification from x times the magnification from y. So the magnification from x, well, let's see. From x, our image distance was 3/2, and our object distance was 3. And then from y, our image distance was 1, and our object distance was 1/2. So we get 1/2 times 2, which is equal to 1. So actually, the two lenses have these sort of opposite effects happening. So there was no net magnification. This is involved too. I wanted to do a tricky optics question. So there it is. Two long wires are separated by a distance d. What is the magnitude and direction of the force? Well, let's just pick maybe the force on one of these wires. You actually should know this. This is just a fact, by the way. You just kind of know what this answer is, but we can do it anyway. So we know that my top wire is going to be producing a field into the page at the location of the other wire. So if I do QV cross B on that bottom wire, the bottom wire is going to get pushed towards the top wire. Now, what's the magnitude? Well, the force on a conductor is BIL. And what is B? Well, B is caused by a wire. So we get mu naught I over 2 pi r, or D in this case, times I times L. So we get an attractive force that sort of looks like Coulomb's law, except there is no square. So this is that kind of counterintuitive fact that like currents attract. Not opposites attract, it's like currents attract. All right, now we're really just so much stuff in physics too. I actually do like this course. It's my favorite of the 4. All right, onto nuclear decay of all things. So we want to figure out sort of what this missing species is in this reaction. So what do we need? Well, first we need to conserve like the number of nucleons. That's checked, right? I have 23 protons and neutrons. But we also need to conserve charge. So we know that whatever this is, it has 0 nucleons in it because 23 equals 23. But what it also needs is we need the charge to add up to 12. So this needs a charge of +1. So in order to conserve charge, we need a particle with no nucleons but a positive elementary charge unit. So that would be a positron. And this is because of charge conservation, not nucleon conservation. Pretty standard there. Oh, diffraction. How could we forget? we got double slit diffraction going on here, where we're just changing the frequency of light, and we're interested in how that affects the spacing of the bright spots, assuming small angle approximation works. So if we look at our equation here, we see that we get this expression, d times y max over L equals m times lambda. So this means y max is proportional to lambda. So y max is proportional to 1 over the frequency. So if we have doubled the frequency, then this means y2 is just 1/2 of y1. And also, this should make sense qualitatively, right? Because if you have a higher frequency, if you've ever done a diffraction lab, you know that the red spreads out, whereas the violet clusters together. So it makes sense that we get tighter spaced maxima. Level 2. Plug and chug thermo. Rectangular slab, we get its area, we have its thermal conductivity. Anytime you see conductivity, you know it's this expression that says energy per time is equal to, look at me, I don't even know my formulas, Ka delta T divided by L. All right, thermal conductivity is 1.5. Area was 4 square meters. What is delta T? Delta T is in kelvins, but Celsius and kelvins are spaced by the same amount. So delta is just going to be 30, 20 to 50. And the length is the thickness of the slab, so 0.5. Let's see, this makes 3, 12. It's the answer with 36 in it, right? Yeah. 360 joules per second, which is a watt. You know, I'm just going to do this because to be consistent. This is plug and chug. 1 star. All right, RC circuit. In the circuit below, calculate the energy stored by the 2C capacitance. Alrighty, well, remember we have 3 energy storage formulas. We have U equals 1/2 Q delta V, which is equal to 1/2 C delta V squared, or 1/2 Q squared over C. Now, there's a couple ways of doing this. The most involved way, we'll just do it the probably routine way, because I don't know if we'll spot some of the things that happen here, is we'll just solve for the total charge. So capacitance adds in parallel, and reciprocal rules in series. So CEQ is just going to be 1/2 plus 1/2 to the -1 times C, which is just C. So that means that we can find our total charge, because our total charge in series with the battery would be CEQ times the battery EMF, or C times script E. And now we can just plug into one of these expressions, and it's definitely the easiest to plug into Q squared over C in this case, because we know that all of the charge from the battery is in series with the 2C capacitor. So there's no junction rule splitting yet. So we'll just say that U is equal to 1/2 times Q squared divided by C, which is 2C for that capacitor. So the coefficient is 1/4. Now there is actually an easy way to do this. This is hard, by the way. There's an easier way to do this. So you can notice that once you see these capacitors are identical, you actually know that the voltage drop must be half the battery across each. So you could have also just said it's 1/2 times the capacitance times the potential difference squared. That gets it done quicker if you can see that. All right. Oh boy, thin film interference, our favorite. All right, thin film. It's constructed on top of a piece of glass with an index of refraction larger than that of the film. So this is a larger n. Okay, so what happens here? Well, anytime you enter a medium with a higher refractive index, you get a phase change. Again, think about that as like when you slam against a wall, you bounce off, and that bouncing reverses your phase. So anytime you go from high to low, and this is a vacuum, so this is n equals 1, this is n equals 1.5, and this is larger than that. So we know that we get a reflect, or sorry, we get, I'm going to say phase. We get a phase shift, and then we get another phase shift. So what this means is that sort of the reflected light would have been phase shifted twice. So this turns our thin film condition into just essentially the extra traveled distance. So our change in path length, our difference in path length is just going to be the extra distance traveled in the film, which is going to be just 2 times the thickness of the film. And there's no phase shifting or anything here. So we can just set our difference in path length to t equal to the destructive condition, where the destructive condition occurs at whole numbers of half wavelengths. So this means that our film thickness should be m lambda over 4, and if we want the minimum thickness, we just pick 1. And it is important that we do lambda in the film here. So this is lambda in the film. And in the film, our lambda is 600 nanometers. It is really important that we pick the lambda in the film. So let's see, 600 divided by 1.5, that's going to be 400 divided by 4 gets us 100 nanometers. How nice, that's an answer choice. Basically anything with thin films is probably 3-star, by the way. Tricky, tricky. All right, Hall effect. Conducting bar moves at constant velocity. We want to compare the electric potential at the top and bottom of the bar with justification. All right, well, QV cross B. My palm is pointing down, so positive charges get pushed down, which means the negative charges would get pushed up. So we can see that the bottom end of the bar is at higher potential, because positive charges in the bar will experience a force in the negative y direction. Yes, we know it's the electrons that are typically moving, but this is just what the justification could be as to why the bottom is higher potential. We don't know. It could be some interesting charge carriers. But that is true. If the positive charges could move, they would experience a magnetic force in the minus y direction. Because equivalently, you could change the statement to say negative charges would move in the plus y, because those two are equivalent. All right, calculate time constant of the circuit below. What is time constant? Well, time constant, tau, is equal to RC, as long as we're doing the equivalent of each of these. So these resistances are in parallel, so we do 1 over 12 plus 1 over 6. And that is equal to, let's see, what is 12 plus 6 in parallel? It's like 3 and 6, which is 2, 4. All right, then we got capacitors in series. Capacitors in series also add by the reciprocal rule. So we just multiply. Our equivalent resistance was just 4 ohms, but our capacitance was 2 times 10 to the negative 6th farads. So our time constant is 8 microseconds. You had to use both rules here, so I bumped this to a 2-star. Two conducting spheres of identical charge but different radii are connected by a wire as shown. The spheres reach equilibrium. Which of the following is true about the potential at the center of each sphere and the charge on each surface? Well, we have conductors that are connected. So we can use one of our fundamental facts that connected conductors are equipotentials. So what this means is that KQ1 over R1 has to equal KQ2 over R2, because the electric potential, KQ over R, must be the same for both of these. So if you had to color their potential, we would see that the potential is actually the same everywhere on the sphere and in the sphere. So how do you get that to happen? Well, we know the potentials are equal, but what about the charge? Well, the sphere 1 has a bigger radius. So if I'm making the same potential, KQ over R, and I have a bigger R, I must also have more Q, right? You got to pack charge, you got to pack more charge on the sphere to generate the same sort of height there. So equal and not equal. The magnetic field through a circular conducting loop is increasing at a constant rate. Which of the following graphs could be the power dissipated by the loop as a function of time? Okay. So we have the magnetic field is increasing at a constant rate. So what is relating to power? Well, we know that the EMF induced in a conducting loop is the rate at which the flux is changing, which is just equal to the area of the loop times the rate at which the magnetic field is changing. And we just said the B field increases at a constant rate. So that means that what we have here is B as a function of t might look something like this. And what's the slope of that? Well, that's constant. So this object right here is constant. So that tells us that the induced EMF is constant. And what is power? Well, power is just equal to EMF squared over resistance is probably the easiest one to look at. So that must also be constant. So since we have a constant induced EMF, we have a constant induced power, making it D. Yeah, this is kind of an odd, novel scenario, so I gave that 3 stars. And then lastly, in the circuit below, X has a bigger resistance than Y. We want to compare the current through each resistor and the potential difference. Well, based on my picture and the fact that this is just a parallel circuit, we know potential difference is the same. And then the current is not, right? Because to create, this is your drive-through, your slow lane. So this is, we should say that this resistance is larger resistance. So you must have less current. You need less current to get the same voltage drop, right? Because if delta V is, or if I is equal to delta V over R, if you have a larger resistance, you must have lower current. Delta I, sorry, larger resistance means lower current. So once you knew that they weren't the same, it's going to be C. 1 star. All right. Yeah, that took about what I thought it would. I think this is maybe a little bit on the hard side, but definitely reasonable. Like, I thought there's some good differentiator questions in here, and overall, I liked this set. I thought this did a good job of including basically everything in the P2 curriculum, and anything I missed, I tried to put in detail on the free response, which you can see coming up here. So, yeah, thought this was a pretty good MCQ section.